So now we'll start the next subsection of the overall controllability topic. Here in this, the next topic is the controllable decomposition, which is written on the top of this slide. And the outline of this section is, so we will cover four major aspects in this controllable decomposition. First of all, the invariance of controllability with respect to similarity transformations. So here the question we want to answer is that if you remember that in the first week we use different representations of the system by computing different ABCD matrices. Now if the question here is, if we have two different AB pairs and they both are related with some similarity transformation, does it also implies that if the first pair is controllable, the second pair would also be controllable? So here we want to show the invariance. The second one is the controllable decomposition. So this is the most important point of this section, where we would going to show that if the system or if the rank of the controllability matrix is not equal to n, then it means that all the states, let's say we would have n number of states, right? That all the n number of states are not controllable. Now the question arises here, that are some of the states controllable? So here we would going to answer that thing by using some decomposition. The third one, we will visualize this decomposition through some block diagram representation. And finally, the equivalence of this controllable decomposition in terms of the transfer functions. Okay, because if you recall from the first week, given two different representations of the same system, we have proved that the transfer function would remain the same, right? Now here the question arises, if I have obtained a controllable decomposed form, whether the transfer function of those two different representations are equal or not. Okay, so this is we would going to answer in the fourth one. So let's start. So we have this, consider the LTI systems. Again, the continuous time and the discrete time are separated by a slash, and we are using this similarity transformation that so we will talk about mostly of the continuous time, because for the discrete time the results would directly hold. If there are some differences in the continuous time and the discrete time, we would take them separately, similar to what we had taken earlier while computing the coherence between the reachability Gramian and the controllability Gramian. Okay, so here we have two different representation, AB and A bar B bar, and X and X bar. So now we have a similarity transformation related by this T matrix, and the property of this T matrix is that it is a non-singular matrix. So X bar is equal to T inverse X. So if I put X is equal to T into X bar into this equation, I would obtain this A bar B bar. And there is also a relation between this A bar A by T inverse AT, and B bar is equal to T inverse B. Okay, so we denote this one as pair A bar B bar of the LTI system, and this one is the pair AB of the LTI. Now we will compute the controllability matrix for both the systems. So this is the controllability matrix of the pair A bar B bar, where we have used all the matrices with the bar overhead. Now in this part we will replace B bar and A bar by these two equations into this controllability matrix. But then you would obtain T inverse B, T inverse AB, and similarly up to the n minus 1. Okay, now since T inverse is common in all these matrices, so I can take it T inverse outside, and the remaining part, if you see carefully, it is nothing but the controllability matrix of this AB pair. Okay, so I can write it as T inverse of the controllability matrix of this pair AB. Now the controllability matrices of the pair A bar B bar and that of pair AB are related again by this simulated transformation matrix T. And we know that T is a non-singular matrix, and if the rank of this matrix, which is composed by matrices A and B, is full rank, that is if it is equal to n, then the rank of this C bar would also be equal to n, because the multiplication of a matrix with the non-singular matrix does not change the rank of that matrix. Okay, so we would have the rank of C bar is equal to rank of T inverse C is equal to rank of C. Okay, the rank condition won't change because T inverse is non-singular. So since the controllability of a system is determined by the rank of its controllability matrix, we conclude that controllability is preserved through similarity transformations. So even if I use any similarity transformation matrix and transform the representation from one form to another form, the controllability is preserved. Okay, and this is the key result, that either you say that the controllability is invariant under any similarity transformation, or you say the pair AB is controllable if and only if this pair A bar B bar is also controllable, where A bar B bar are specifically given by or in terms of AB and the similarity transformation matrix. So the proof of this theorem is in fact given above. So we started with so this is what we call the proof by construction, and then finally give the result. Okay. Now coming on to the controllable decomposition part. So consider again the LTI systems. Note that here that the controllable subspace C, this is mathcal C, of the system AB LTI is invariant, A invariant, and contains image of B. Okay, what does it mean? Try to visualize this thing, that the image of B is in fact a subset of this controllable subspace. So any vector or any element belonging to this space would definitely belong to this subspace, and this subspace is A invariant. So you can take this, you can prove it by yourself. So you can take this as an exercise and show it by yourself, that the controllable subspace C, which is, and C, if you recall from one of the result, that C is nothing but equal to the image of the controllability matrix. Okay, and this image of this controllability matrix contains this subspace image of B. So in fact the proof is pretty much straightforward. But you can show this, the first part A invariant, we have already shown that this controllability matrix is A invariant, right? So you can take this as an exercise and see and solve by yourself, or to prove this property. Now because of the invariance of the, or A invariance of this subspace, we can construct a n cross n bar matrix V, where the n bar is nothing but the number of columns of V matrix, yeah, whose columns forms a basis for this controllable subspace. This is in fact the one of the first property of any linear subspace being A invariant, or any matrix invariant. Here it's A. So there exists an n bar cross n bar matrix AC such that this equation has been satisfied. Okay, AV is equal to V into AC. Moreover, since the image of B is contained in the controllable subspace, we know that the columns of B can be written as a linear combination of the columns of B. Now if it can be written as a linear combination of the matrix B, I can write it as B is equal to sum V into BC. Okay, so meaning to say that therefore there exists an n bar cross k matrix BC such that this equation is satisfied, and this is nothing but saying that B is a linear combination of all the columns of V. Okay. So now this is an important point, that when the system ABLTI is controllable, you would have n bar is equal to n, which is nothing but the dimension of the controllable subspace. And the matrix V in that case would be a square matrix, because the dimension of matrix V is n cross n bar. And V would be a square if the system is controllable. Now here the question arises with what we have started, that if the system is not controllable, then let's say we define a matrix U. If the system is not controllable, it means that the rank is not equal to n, but it is less than n. Okay, so we define another matrix U, which is an n times n minus n bar matrix, whose columns are linearly independent of each other and also linearly independent of the columns of V. So this U matrix has these two properties, that all the columns are linearly independent to each other and also to the matrix V. So using these two matrices U and V, which we have defined earlier, I can write another matrix T, which is a non-singular matrix given by cascading this V or concatenating these two matrices V and U. V is a n cross n bar and U is n cross n minus n bar. So the overall matrix would be a square matrix of dimension n. Okay. Now see here that the multiplication of the matrix A into T I can write as equal to A into V U, taken from above. And since both of them are matrices, I can individually multiply this matrix with these matrices. So I would have AB and AU. AB, by using that property, I can write as V into AC. And since T is non-singular, T into T inverse would be an identity matrix. So I have replaced identity matrix by T into T inverse into the second part. Okay. Now V into AC, I can write it as T and this matrix. Let's see if you have faced any difficulty, that T is your VU. And this matrix is AC0. So this matrix is nothing but V into AC. Because U into 0 would be 0. Right? So I can write V into AC as T into this matrix AC0, and the rest part would remain as it is. Okay, so the path from A into T to this is clear now. So moving forward, that this part T inverse AU, I can partition this matrix as A12 and AU, arrange in the column. So finally I can write my matrix A times T is equal to T taken common from this part AC0 and taken from this one, which is nothing but T into A12 and AU. So the remaining matrix would be AC0 and A12U. And B, we already have V is equal to V into BC. And similarly, as we have seen here, I can write VBC is equal to T into BC0. Okay. So now comparing, we could write this matrix AC A12 AU as equal to T inverse AT and BC0 as T inverse BT, where T is nothing but a non-singular matrix, so it happens to become a similarity transformation with respect to this T matrix. So we just have constructed a T matrix given the matrices A and B. Okay, so this part is called the controllable decomposition. We will explore further properties, that with the introducing this specific T matrix which is given by here, we have decomposed the A B matrices into controllable decomposition. So note that here that it should be clear from the visualization also. So suppose if we have this A bar matrix and we say this is a B bar matrix, and say suppose we denote XC and XU. Okay, here we would have AC, A12, 0, AU, XC and XU plus BC0, U. Okay, so here this is also called a canonical form, by the way. Why? Because you see that this XU state is not at all influenced by U, and it does not have any dependence on XC, on which U has an influence. Okay, so basically we are trying to go towards the path where I can extract the controllable part from the given AB pair. Okay. So recall these two matrices we have just constructed. So for every LTI system, AB LTI, there is a similarity transformation that takes the system to the form 12, which is the decomposed form, for which the controllable subspace of the transformed system is given by the image of this identity in 0, and this identity is having a dimension of n bar. Okay, and the pair AC-BC is controllable. Okay, now just visualizing this result, the question what you ask from yourself, that if I want to compute the rank of this AC-BC pair, the rank would be equal to nothing but n bar, and n bar is less than n. Okay, so this form is often called the standard form for uncontrollable systems, because we already know that n bar, which is a lesser number than n, meaning to say that the system is not controllable. So it is the standard form for uncontrollable system by introducing a specific similarity transformation matrix T. Okay, so in the MATLAB you can also obtain this decomposition by using this CTRBF command, okay, which computes the controllable decomposition of the system with realization ABC. So A bar, B bar, C bar would be of this form, and it would also give you the T matrix which we have computed by a combination of V and U matrices. Okay, so next we'll see the proof of this one, that how it becomes the rank of this control, or let's say the dimension of this subspace is equal to n bar. Okay, so to compute the controllability subspace of the transformed system, we compute its controllability matrix, which is the C bar. Now here I have written all by opening all these A bar, B bar matrices. So earlier when we studied this controllable decomposition, we had our results in terms of bar matrices over it. Now here we know that bar matrices are nothing but these parts. Okay, so this one would be this one. So here if I simplify this matrix, I would have AC-BC plus A12 into 0, 0 into BC plus AU into 0. So the rest term would be AC-BC in 0. Similarly, if I go forward, I would have AC to the power n minus 1. Why? Because this is an upper triangular matrix, and the power of the upper triangular matrix would be the power of the diagonal elements, and the off diagonal elements would be computed. So that's why we have written AC to the power n minus 1 directly. If there is some element, some non-zero component here, then I could not write it AC to the power n minus 1. Okay, so this point should be noted here. So AC to the power n minus 1 BC. Okay, now this row is completely 0, so this won't contribute any in the rank. So since simulated transformation preserved the dimension of the controllability subspace, which was n bar for the original system. So we would have rank of C bar is equal to n bar. Once we have, because we already know that there is the rank of this controllability matrix is n bar, which is less than n. So the dimension of that subspace is n bar already. Now we have extracted that subspace in terms of this controllable decomposition, which says that the rank of the C bar is nothing but equal to n bar. So since the number of non-zeros rows of C is exactly n bar, all these rows must be linearly dependent. Therefore, we would have image of the C bar is equal to the image of the identity matrix or dimension n bar and 0. The rest of the for the rest of the dimension. Okay. Moreover, this one is also already equal to n bar, which is not equal to n bar, n. Otherwise, the system would have been controllable. And since AC is a square matrix of dimension n bar, then again by using the Cayley-Hamilton theorem, we would have the rank of this one equal to the rank of this one, because this won't contribute into the computing of the rank. So the rank of this rest of the matrix is n bar, which proves that the pair AC BC is controllable. Okay, because we have extracted or we have discarded the matrices which were contributing towards the failing of the rank condition. Okay. After seeing this, the controllable and uncontrollable decomposition of the pair AB, we can go back to the same representation what we have discussed previously. So let's see here. We have this the LTI system, continuous and discrete both. Here T is a simulated transformation matrix which decomposed the pair AB into this one, and this is nothing but your A bar pair, A bar, B bar and C bar. Okay, and partitioning the state of the transformed system as this is XC and XU. So the idea of introducing this C and U in the subscript of the matrices and the vector from the beginning is to come to this point where we can explicitly show that which states are controllable and which states are uncontrollable. Okay, and with respect to those controllable and uncontrollable states, what are the associated matrices? So AC is associated with the matrix with the vector XC, and AU is associated with the vector which is uncontrollable, state vector which is uncontrollable. Okay, so we have x dot c, x dot u. This we have seen already. So again, I would like you to pay attention here that x dot c is being influenced by both the controllable and the uncontrollable states because of these two, say for example, non-zero elements. Okay, and it has a direct influence of the control signal U because of this non-zero BC matrix. Okay, now XU is only triggered by its initial condition, not by XC, and it does not have any influence by U. So basically it is nothing but a homogeneous equation. X dot U is equal to AU XU. Okay, now so suppose if we have some non-zero element here, okay, if we have some non-zero element say for example if we have a B matrix as it is being the zero element here, now if this element is also non-zero, if this element is non-zero, it does not imply that XU would be uncontrollable. Why? Because in that case XU is being influenced by XC and XU, where XC itself is being influenced by U. So this could be an or loosely speaking could be an indirect control of the XU, right? So here we can see straightforwardly that u and xc does not have any influence of xu. So this part has been completely removed from the controllable representation. Okay, the D matrix won't change as we had seen in the simulated transformations. So if I draw the block diagram here, so this part we would have BC into U, and this part is being added, which is A1 to XU. So the addition of this BCU and A1 to XU, we have replaced it by nu. Okay, so this nu is nothing but your BCU plus A1 to XU, and the rest is ACXE. Multiplied by CC, we would have the Y matrix. So you would see that XC is only being influenced by U. Okay, and XU there is no or you can say it's by the 0. So this is the uncontrollable part, because you cannot control, since the input would always be 0. You cannot manipulate the input. Okay, so there are 2 points which should be noted, that this figure highlights the fact that the input U cannot affect the XU, because if you notice, starting from U there is no direction which is going towards to XU through any path, right? The second point is the controllability of the pair ACBC means that XC component of the state can always be taken to the origin by the appropriate choice of U. Okay, which is basically the definition of controllability. Right? Let's see the transfer functions. So since the similarity transformations do not change the system transfer function, this is we had seen in the first week when we were discussing about the equivalence transformations of the two different pairs. So if we compute this TS, which is your C Si minus A inverse B plus D. So this is the overall transfer functions we had computed. So again, since it's an upper triangular matrix, so the inverse of this matrix would be the inverses of this diagonal elements at least, and this off diagonal element we can write, or it needs to be computed, but it is of no use to us because the multiplication of this with this would be 0. Okay, so finally we would have this one, CC Si minus AC inverse BC plus D. Right? So since you can also use this property that whenever under any simulated transformation, the transformation does not change. So once we have the explicit representation of the controllable and uncontrollable representation, and we know that transfer function is basically the representation only of the controllable part of the system. What it also implies that whenever a transfer function is given to you, that those transfer functions are always controllable. Okay, so if a transfer function is given to you, those plants are always controllable. Okay, and this would nothing be equal to the transfer functions of the original system. So it says, this shows that the transfer function of the system is equal to the transfer function of its controllable part. So this is the important conclusion. Now if you can see that if a transfer function is given to you, or a matrix of transfer function is given to you, which we would possibly discuss in the last week when we discuss of the MIMO systems explicitly, then those systems are already controllable, right? Because the system has been represented through transfer functions only. Okay.